Day 45, weight versus map. Would you please pause the video and first try the warm-ups? Try them all on your own first and then play the video to check your answers. So at this time you should have all your answers now to the warm-ups. Weight is the force of gravity on an object. Weight is the force of gravity on an object. Mass is the amount. Mass is the amount of stuff in an object. If an astronaut goes up to the space station, does their mass change? No. They have not left any body parts on the launch pad. They have just as many cells in their body up in the space station as they did on Earth. So their mass does not change. The amount of stuff in their body, they do not shrink or expand. However, number 4, if an astronaut goes up to the space station, does their weight change? Yes, indeed. The force of gravity becomes less as you move farther and farther away from Earth. So the force, the weight changes. Number 5, find the force of gravity on an 80-kilogram person on a space station that is 330,000 meters above Earth, and Earth has a radius of 6,371,000 meters. So we're going to use Newton's law of gravitation. F equals G mm all over r squared. The G is 6.67 times 10 to the negative 11th. The capital M is the mass of the larger object, which in this case is Earth. And we've learned in our previous notes that Earth has a mass of 5.97 times 10 to the 24th. The little m is the smaller mass, which is the 80-kilogram person. And at the bottom is the radius of the orbit. That's the distance between the center points, between the cores. So we have not only the radius of Earth, but also a little bit above Earth that the space station is. So I have to add these two together, and I get the distance between the person and the center of Earth being 6,701,000 meters. And we're going to square that. If you type that into your calculator correctly, you should come up with 709 newtons. So there is a force of gravity on astronauts on the space station. What is the effect on this force? It keeps the station in orbit. It prevents it from floating off to the moon and beyond. So there is a force of gravity on space objects that are in orbit around Earth. That's what keeps them in orbit, what keeps bending their path to go around and around Earth. So instead of saying that astronauts are weightless in space, we should say that they feel weightless. Find the weight of an 80-kilogram person on the moon and on Earth. Now in this case, we are on the surfaces, and so we're just going to take the radius of the two bodies and have that as the r value. We do not need to add this orbiting height. Okay, so on Earth we have F equals G mm all over r squared. The G is 6.67 again, times 10 to the negative 11th. M is 5.97 times 10 to the 24th. That's the mass of Earth. And then the mass of the person is 80. And then the R value is just Earth's radius, 6,378,137. A little bit more precise this time. Up here I had a rounded value. If I do all that math, I come up with 748 newtons. So when we're on Earth and we're a little bit closer to the cores, it's a little bit higher than when we were up in the space station. So when you go up into the space station, you do lose some weight, but it's not dramatic. The reason why it looks so dramatic is because the motion of the space station is the exact same as the motion of the astronaut, and that's why they can float around. The astronaut can float around inside the station. You can imagine an elevator being sort of like the space station. If you're in an unfortunate circumstance of being in an elevator and the cable snaps and the elevator starts to plummet down, you can imagine that you'll be apparently weightless in the elevator as it plummets. You'd be able to float around in the elevator just like a astronaut in the space station, because you are falling downwards just as fast as the elevator is falling downwards. In a similar way, the space station is going around Earth in the exact same way as the astronaut is going around the Earth, and so the astronaut can float around inside the space station. Okay, moving on to the next one. F equals GMM all over R squared. Putting in these numbers, you should get 129 newtons. So about 1/6 of the force of gravity. Main ideas from last lesson. Gravity is a field force. Field forces affect objects without the objects touching. Electricity and magnetism are also field forces. Field forces have the same basic equations. The distance between the object centers is in the denominator, shown as r squared. The sizes of the objects are shown in the numerator. The object's size and gravitational force are directly proportional. When one changes, the other changes in the same way. The relationship between distance and gravity is an inverse square law. The force changes in the opposite way and much faster than the distance changes. A small decrease in the distance will lead to a bigger increase in the force. Today's grades, we just have homework 45 to do, and we'll be having a quiz in a couple days. The purpose of today's lesson is to learn to tell the difference between mass and weight and how to calculate weight. Relevance, people often get these two things mixed up, and it's pretty easy to do. So we're going to get that straightened out. Success, when given an object's mass, I'll be able to calculate the weight. Mass is how much stuff is in an object. Weight is the force of gravity on an object. Imagine finding the weight of objects with the following masses on the surface of Earth. We would apply Newton's law of gravitation with the mass of Earth, the radius of the Earth, and the mass of each object. So we would be doing this kind of a calculation for each one of these. Let's see here. F equals G capital M little m all over R squared. 6.67 times 10 to the negative 11th for the G. For the capital M, we're going to have 5.97 times 10 to the 24th. And then we're going to have the mass, whatever that is, for each team. I'm going to put a question mark for now because it's going to be each one of these numbers divided by R squared. That's 6378137 squared. So each team, when they do these calculations, they're going to be multiplying all these numbers and dividing, plus, or I should say, and also multiplying by these masses. So team 1, you're going to, instead of the question mark, they'd put in 40. Team 2 would put in 87 for the question mark. And when you do that, here are the results. 391, 851, 283, 910, 988, and 1262. These are all newtons. So these are the forces of gravity on these size objects when they're sitting on the surface of Earth. To get these numbers, we did virtually the same thing each time. We multiplied that times that, divided by that, and we multiplied by the mass. So instead of having to do this all the time constantly, let's try to reduce things down and get a simplified version of this equation just for this kind of a problem. So we're going to use Newton's law of gravity to find an equation for the weight of an object at sea level. Use F sub W for weight. So F sub W, GMM divided by R squared, F sub W is equal to 6.67 times 10 to the negative 11 times the 5.97 times 10 to the 24th times the little m divided by 6,378,137 squared. Well, if I do all of this together and I leave the m, I'm going to leave the m as a letter, but I do all this in my calculator. Guess what I come up with? 9.8. Does that look familiar to you? I sure hope it does. That's the acceleration of gravity. And so we could write this as F equals AM, or in other words, F equals MA, where the A is the acceleration of gravity, 9.8. So anyway, here we have a shortened equation that is just to find the force of gravity on an object with a certain number of kilograms. You have to have the mass in kilograms. Find the weight of a 5 kilogram object at sea level. So F sub W is the weight, 9.8 times 5. Multiply those together and you get 49 newtons. Newton is the unit for force. It's also the unit for weight, because weight is just another version of forces. Find the mass of an object that weighs 62 newtons. So in this case, this is the F. We're looking for the M. F equals 9.8 M. That's an F sub W. We're going to put in a 62 for the F. So we have 9.8 times M on the right-hand side. We're going to divide both sides by 9.8. 62 divided by 9.8 is going to be 6.3. And that's going to be newtons. Number 12 and 13, would you please pause the video, try those out, look at your neighbors, see if they get the same answer, and then play the video and see if you get the same thing as me. The 131 is the weight, or the force sub W. So I put the 131 for that. Divide both sides by 9.8 and you get 13.4. And kilograms is the unit for mass. For number 13, find the weight. So we're going to find the F sub W. 9.8 times the mass, 0.7 kilograms. So just straight multiplication there, and you get 6.86 newtons. Number 14, what kind of mathematical relationship exists between weight and mass? It's a direct relationship, directly proportional. What that means is if you double the mass, you're going to double the force of gravity. If you cut the mass to be a third, then the weight, or the force of gravity, becomes 1/3. And here's another example if you want to look at that.